So that's a little intro to how to do these. But let's talk about the game plan in general. How do we solve simple harmonic motion problems and find omega? There's two main strategies that we're going to talk about. The first, which we've talked about at the very beginning here, with our first problem, is we can do sum of the forces equals ma. And the second way is we can find the energy equation and set the time derivative of the energy equal to 0. The next thing we'll do is we're going to rearrange our equation so we can make it look like this, where we have the second time derivative plus something times x equals 0. That something times x is always going to be omega squared for simple harmonic motion. It's that simple. All you have to do is rearrange your equation so it looks like x double dot plus some coefficient times x equals 0, and that coefficient of x is always going to be omega squared. All right. Should we try flexing our problem-solving muscles now? I will leave this up. All right. Our next example. Let's imagine that we have a spring and we have two identical masses on either side, and they're sitting on some sort of frictionless table, so we don't have to worry about any of those forces. And we're going to pull it apart, and we're going to let it go. And we want to know, what is the angular frequency of oscillation going to be? All right. So if we pull, let's see, the right-hand side 1 by x1, the left-hand side by x2. Yes, question?
You said, why do you think dE dt equals 0?
Why is dE dt equals 0? Anybody want to take a shot at that? Conservation of energy. Yeah, so this is so long as there aren't any non-conservative forces acting, energy is going to be conserved, and so dE dt is going to be 0. Any other questions before we move on? Okay. All right, so here we're going to pull our masses back. We're going to pull the right one by some distance x1 and our left one by some distance x2. So if these are identical masses, what do we think we can say about x1 and x2? How much each one's going to stretch the spring? They're going to be equal, right? That's nice. Okay, so the way I want to solve this problem is with the dE dt method. So let's write down the energy associated with these masses. So at any particular point in time, these blocks are going to have some kinetic energy. What other energy is going to be in the system? Okay, what's the energy of the spring? Okay, what is x? What do I write here? How much is the string stretched by? 2x. Yeah, so here is stretched by x1 plus x2, quantity squared. Because this is the total energy in the spring. So you're not doing 1/2 kx1 squared plus 1/2 kx2 squared. It's really the total stretch of the spring that's holding this potential energy. Okay, so now let's simplify this a little bit. We have set up there that x1 equals x2. So let me just call that x. If the x's are equal, then that means that the velocities, the magnitudes of the velocity, I should say. So these are the speeds. The speeds are actually going to be equal. Okay? So if I plug that in here, it's going to be a little simpler. Okay, so this is 1/2 mv squared plus 1/2 mv squared. That's just going to give me, oh, you know what? Let me call this instead x dot, just to keep with our same notation. Okay, so we have two of these, so the 1/2s go away. So I'm going to have an mx dot squared plus, let me see, 1/2 k times 2x squared. That's just going to be mx dot squared plus, let's see, that's 4 times 1/2, that gives me a 2. Right? Okay, so now, I'm going to ask you, I've got you set up. Remember, we're going to set d dt equal to 0. So I want you to work ahead of me here. What is going to be the angular frequency of this oscillation?